Here we go. Okay, so question 1. Question 1. Now, there's a word here, well, there's many words here. This thing here, diffraction grating. This word here, diffraction, that's the name you give to the phenomenon of wave. You know, when a wave passes through a little gap like I drew earlier, it spreads out. Okay? This spreading out, that's called diffraction. Diffraction. So if I'm saying wave diffraction, it means wave spreading out. Okay. Anyways, what do you think of would you know what you would know what a diffraction grating is? What about Louise or who? Would you know what a grating is? This word in English, grating. You know it, don't? No. Louise, do you know this word in English, grating? A grate? Grate. Yeah, do you know grate? Grate, as in G, not G-R-E-A-T, not this grate, the other one, G-R-A-T-E. Do you know what this grate in English? No? This here means, like a grater, like a cheese grater, yeah. A grate is something that looks like this with lots of bars on it. You know what? I think a cheese grater is a good picture to show you. Do you make anything at home with cheese? Yeah. So how do you live then?
You take the cheese, then the whole cheese?
You know when you want to make the cheese like
on the pizza or something?
Okay, actually I will buy some.
You buy it just to happen.
Do you know when you have the cheese and then you go like this and it falls down?
Powdery.
Do you know this too?
Yes.
You don't know this? Do you know what I'm talking about?
Anyways,
grating is when you have lots of these little bars together. So I can give you a good example. You know, on the side of the street, there might be a hole in the ground for where the water goes into it. You know, at the side of the road for the water. Yeah, it's like a rectangle on the ground. You know what I'm talking about? And you got the idea. Do you know the word for Louise in Chinese?
In Chinese?
Go ahead, just that one word in Chinese. Why do you need to draw a picture if you're giving her the word in Chinese?
Maybe I don't know.
Okay, go ahead. Yeah. Did she got it? You don't got it?
It's that some people it's cross the road and then the car.
No, not this. No, not this. This is a zebra crossing. No, but anyway, it doesn't matter. I'll get a picture later and I'll show you a picture, okay? But for now, all we need to know is that it's just diffraction grating is just lots of these little bars put together. Okay, so, you know, you could imagine, it looks like this, okay? And then imagine you cut lines down it. So there's lots of like little strips cut down it. So you could see through it, like bars. Okay. Now, it says in the question here, the diffraction grating has 500 lines per millimeter. So that means you have 500 lines in 1 millimeter. So who could tell me what the distance between each line is? Well, what would it be? Yeah, the distance here between the bars is 1/500 millimeter. Okay. You're also told that the n is 3. And you're also told that the wavelength is 620 nanometers. Oh, I don't have any question, do I? Well, the question would be what's the angle?
Yeah.
Yeah. So the question here is what's the theta? Can I scroll down a bit to draw this? Yeah. So look, it's just like what we had earlier today. You have the light, and then the light goes through these bars, and then the light spreads out. You know? So they want the angle here for the third dot, n equals 3. They want the angles. Doesn't matter, my drawing's terrible, but what formula do we need to use here? Yeah, it's the d sine theta equals n lambda. So the d we said is 1/500 millimeters. So that's 10 to the minus 3. Sine theta we don't know, the n is 3, and the lambda is 620 times 10 to the minus 9 nano. Yeah. So sine theta equals 500 times 3 times 620 times 10 to the minus 9 all over 10 to the minus 3. So on your calculator, can you just give me that fraction?
3 or 6?
Sorry, I said 3 and everything, didn't I?
Yeah.
3. So what fraction do you get there? Sorry, do you have the number? Not yet.
0.93.
0.93, is it?
Yeah, it's 3
So what's the theta? 68.4 degrees. Okay, so that's the first one done. Number 2. Can I go down to number 2? So number 2 is asking you for constructive interference. So who? Do you remember from this morning what is constructive interference?
Two are together.
Two what are together?
Two waves.
Yep.
And they make a bigger wave.
Yeah, that's it. So constructive interference is when two waves come together and they form a bigger wave. Now, here's a word I didn't tell you. Coherent. Does anyone know what that means? Would you remember coherent?
You remember the picture?
I'll help you.
It's like there's this constructive, destructive.
Let me help you. Two waves are coherent if they're the same frequency and in phase.
So what's that thing called?
Which one?
Like there's one where it's two and there's I remember the picture, but I can't remember what it's called.
I don't know.
So so if you draw a line through any points on the diagram, on the image, it will always go constructive. Kind of like it was like a diffraction grating, but it was two sources.
Yeah, well that's where the coherent comes into it. When we talk about Young's experiment, the two are coherent.
That, but
Yeah, well, it is that. It is exactly that, yeah. But I just wanted a simple English for it. So we say two waves are coherent if they're the same frequency and they're in phase. Do you remember what in phase means from this morning? Louise, do you remember in phase? Yeah. Do you remember? Yeah. For the wave, what does it mean? If I say two waves are in phase, what's the same? Be exact, what's the same?
The wave curve is same.
Yeah, you're so close. Yeah, give me some more words here. So what is the same? Oh, she'll get it. No, don't look at him. You don't want to look at him. Louise, what's the name of the top of the wave? Do you remember this? Huh? Peak, yeah, there's another word for it, but peak is fine. And what's the name of the bottom of the wave? Yeah, what is it? T sound. We call the bottom of the wave the trough. And on the top we call it the crest, or the peak. So if they're in phase, what do we know about the crests and the troughs of the two waves? Yeah? Help her out, Bill. Do you remember?
She does, she's about to say it.
Go ahead, say it. What do you think?
Say what you're about to say.
You're making her nervous. Relax.
Yes.
You're making her nervous. Yeah.
Orange is the key.
No, you're making her nervous. Just relax. What are we going to say, Louise? Go ahead. Describe it. Don't worry, it's only the three of us. Yeah? Yeah. So look at your, let me help you. So where's your graph for in phase? Here it is, here, in phase. So, what was I saying when I was drawing these arrows here? What was my meaning?
Because the curve is same.
Yeah, that's it. Yeah?
Because there's the red curve and the blue curve.
Yeah. So, here, this is a crest, and this is a crest. And what I'm saying was the crest here and the crest here match up. They're at the same place. And then the trough here and the trough here, they match up. They're at the same place. This is in phase, and then this is out of phase.
It's because, but they also is the center is something like that.
Yeah? Go on.
Actually, the two curves is same, but one is the top.
Yeah, one is the top,
One is
the crest,
Yeah, the crest.
and the other
Opposite.
is what's the opposite called? The trough.
The top. Okay.
Yeah. So this is out of phase, and then this is in phase. Yeah. So what I'm saying, this word here, coherent, means in phase and the same frequency.
So it's between this.
Yeah, that's an example of coherent. And then what's the opposite word to coherent? What's the opposite of coherent? Don't you say it? What's the opposite? Yeah. What's the in English? What do you think the opposite of coherent is? The opposite word of coherent.
Coherent.
Yeah. What's the opposite of coherent?
Distraction.
No. Simpler. Coherent and uncoherent, or what do you say? New?
Incoherent.
Very good. Incoherent is the opposite. Okay, so coherent and then incoherent. Yeah. How did you know it was in and not on? Or this, yeah, discoherent or uncoherent.
Oh, try all three. Which one sounds the right way?
So you were just going to try first with incoherent and then discoherent and then uncoherent, was it?
Anticoherent.
Oh, yeah. Good, yeah. Okay, so we understand what coherent means, yeah? Okay, so let's go to the second part, the calculation. So for the second part here, you have the wavelength equals 628.3 nanometers. The spacing between the slits, the D, is 0.125 millimeters. And the big D, the distance between the source and the screen, so the big distance, that is 1.25. So I'll just roughly draw this here. So you have here the first one, n equals 0, and then you have one here, 1, 2, 3, 4. N equals 4, n equals 3, n equals 2, n equals 1. So their question is they want to know the distance from the central fringe to the fourth fringe. Louise, what does this mean? What's this one? What's this called? This one here. Not theta, no, that's the angle. What's this one for? What do we use it for? Yeah. Not frequency, no. It's not theta, no. It's wavelength. Wavelength, yeah. And then who? What about this one? What's this one to measure? What's this one for?
The distance, the small distance.
The small distance between the slits, yeah. And Louise, this one here is the wavelength for the wave that comes in. The wavelength. The wavelength. And then, Ugo, what's this big D for, the 1.25 meters?
This is assuming the slit and the...
Yeah, it's this distance here. Okay, and they would like to know this distance. So what formula could you use? Yeah, in fact you can use both formulas, but the easier one to use is the second one I gave you, which is what? S equals small over big or big over small?
Well, that's what you gave us.
Yeah, well, that's what I gave you, it's right then.
Yeah,
Big over small lambda. So do we know the S? No, we don't. Do we know the big D? Yes. The small d? Yes. And the wavelength? Yes. What does this S represent? Yeah, the S is all this distance. They're all the same, roughly. This is all the S. So how many S's do I have to the fourth dot? 4 S's. So once I get the answer for S, I just multiply it by 4 and I'm done. Okay? So we need our calculators here. 1.25 times 628.3 times 10 to the minus 9 all over 0.125 times 10 to the minus 3. What's that, please? That's it. 6.283 times 10 to the minus 3. So my answer is 4S, which is
0.025132.
Okie dokie. Sorry about that. 0.0.
25.
Yeah.
132.
Meters, which is 2.51 millimeters. Isn't it? Isn't it? It is. Yeah. It is, isn't it?
I think it's 25.
Millimeters.
Yeah.
Sorry, of course, because... Sorry. 2.51 centimeters. Okay, so just before I let you try these for a few minutes, I just want to make sure you understand all the variables in the picture. Can I scroll down? Okay, so I can scroll down, yeah? Okay, so what you have here is you have a wave coming in, and then it passes through usually 2. Well, I mean, you can have more, but what will happen is it'll pass through, let me draw in green, 2 of the slits here. And then it will spread out. And then on the wall here, you'll have a dot here, then a dot here, and then a dot here, and then a dot here, and then a dot here. And then, okay, so what we'll do, I just want to make sure you understand all the letters. So let's see, Louise, what is this here? Sorry, so let me write all the letters on the side for you. Do you know it? Wavelength, okay. Then I don't need to write them, so that's wavelength, okay. And Ugo, what's this one here? Big or small? Small. And then, yes. Hey!
Hi, sorry to interrupt
Want
you.
some
Nick,
business?
how are you?
I know, it's okay.
No, you finish your point.
I don't know, it's okay, it's okay.
Are you sure?
Yeah, it's fine, yeah.
It's you I'm looking for.
Oh, yes,
Yeah.
do you want to talk outside, or?
Well, I can speak to you.
Oh, yeah, okay, I'll do the time table,
Thanks,
yeah.
Matt. So this Monday, I want to...
Yes, sure.
So all I could find was 1 hour where you have them all together, and then to make your constitutorial on Monday, double with both groups.
Okay, so,
That's what I'm asking.
yeah, so it's 9 o'clock, yeah, 9 o'clock I have
Now, you're
maths.
going to 7 hours on Monday.
Yeah, but that's okay, just run with the 1 hour. Yeah, then a double, yeah.
Sorry, the 1 hour in both groups is another day. That's here on Wednesday. So I've squeezed in an hour there.
Great.
2 and 3 is great. And then on Monday, I'm going to take longer, so you have an hour there.
Yeah,
And a
and
double.
then a double, and
Then
then,
I've moved your math there from here up to here.
yeah, so it's
And you
single,
have an hour, just
then
back for lunch.
yes, and then that's single with the other half.
Yeah, and
yeah.
then a double then.
Double with,
January 21.
okay, and January Science 2 have a double as well, okay.
So
Okay.
you get 1 additional tutorial and 1 additional group hour with science and engineering in
Okay,
January. So that'll be a total of 2 hours.
great,
So that'll be
great.
enough to think
Oh,
about.
yes, yeah.
And if you really feel the need to have got them happening on Thursday, you could keep them forever if you want.
Yeah, yeah. Would you like to do maths until about 6 or 7 on a Thursday? 10? Yeah? I wouldn't be. Yeah, that's fine. Will I tell them, or do you want to email them?
Actually, I'll email it out. But just to let you know, guys, to come in on Monday, if you're in group 2, are you group 2 or group 1? You're both group 2. So you have speaking exams on Monday for your EAP class cancelled. So you don't have the AP on Monday at 9, but you'll have a double maths tutorial team that starts at 10, 10 to 12. I'll email it to you as well. And you
Nice, yeah.
will have double maths from 3 to 5 on Monday.
Yeah. It's a double tutorial as well, okay, so we're in a small group for it.
Okay.
Alright, thanks, Emer.
Sorry to interrupt.
Oh, no, that's okay. Alright, you okay? What did she do?
She put me on.
Now where was I? Oh yeah, okay, so we have that one, and Ugo, you gave me that one, okay. So we'll go back to Louise. So Louise, what's this one here? Big D, yeah, okay. And then who? What are these distances here? Is F, yeah. Did I leave anything out? Oh yeah, you can also have like the angles, yes. You know the names this here, Louise? Theta is for measuring the angles. So I mean, I think this question is not too difficult once you practice the formulas. It's actually quite a short question to do. Yeah? So I've just done number 1 and 2. So what time are we at? Okay, good. So what I was thinking was maybe for about 8 minutes or so you could try some of them, and then for the last 10 minutes we'll talk about the final point, the final worksheet. Did I give you both worksheets? Oh, right.
No.
I need to print the second one. Okay, so while you I'll print them and give them to you in math class. Yeah. So work on these questions for a few minutes, and then we'll look at the last page. Okay, so number 3.
I can do it right.
Well, it's okay, we'll do them anyways. So number 3, in Young's double slit experiment, distance between the slits and the screen, okay, so, yeah, oh sorry, thank you. The D is 0.85. The lambda is 630 times 10 to the minus 9. The distance on the screen from the central maximum to the third. So the S is 4.27 divided by 3. Because what they're saying in the question is the distance from the center to the third dot. So the S is divided by 3. Milli, is it?
Yeah.
Okay. What do they want? Oh, the D, yeah. So you have lambda equals D over D, no, sorry. S equals D over D lambda. So then D equals D lambda over S. So the answer is D equals 0.85 times 630 times 10 to the minus 9 all over 1.4. And this comes out as 10 to the minus 4. So that's 0.376 millimeters, isn't it? 0.376 millimeters. Right. 0.376 millimeters. The next part, the only difference, literally, the only difference in the next part is this 630 is replaced with 540. That's the only difference in the next part. So if you replace it, what do you get on your calculator now for part 2? Should be about 2.76, no, not that much smaller. It's about 3 times 10 to the minus 4, is it? Yeah, tell me what you get, please. Yeah, so in this case you get 3.23 millimeters. Sorry, 0.323 millimeters. Alright, let's have a look at 4. So number 4. A purple light contains red and violet spectral lines. A purple light source containing red and violet spectral lines is incident normally on a plane, transmission grating. The third order violet line coincides with the second order red line at 40 degrees. Now this one's a little bit more complicated. I think we'll just finish with this one. So what they're saying here is you have 2 lights, a red one and the violet one, which I'll just do in blue here. And the red one has a dot, a third order dot here at an angle of 40 degrees. And the, oh sorry, that's the other one, sorry. The violet one has a third, hits here when n is 3 and that's 40. But they say that coincides. Who knows what coincide means? You should know coincide. Do you know this word in English, Louisa, or who? Coincide? Coincide means the same place. So they're saying that the third order violet coincides with the second order red. So the red one is also here, but for the red one it's n equals 2 but the angle is also 40. So you have the red and you have the violet. You also know that the D is what? Oh, you don't know the D, but you know the wavelength, huh?
No one.
The wavelength for red is 620 nanometers, and then the wavelength for violet, you don't know. That's what you want for the first part. Okay, Louise, for the red one, what's the N? It is 2. And then, do we know the wavelength for the violet? We don't. We don't know it. But we do know the N. What's the N here? Is 3, yeah. Now, do we know the small d? Do we know the small d?
We know they're equals.
No, we don't know what it is. And the other one, we don't know what it is. Do we know the angles?
Yes.
Yeah, the theta is 40, and here the theta is 40. So, we can use our formula. N lambda equals d sine theta. So d equals n lambda over sine theta. And here n lambda equals d sine theta. So d equals n lambda over sine theta. Now, what's the n here? 2. The lambda, 620 by 10 to the minus 9. And then this is sine 40. And then here, the d equals 3 lambda over sine 40. We don't know the wavelength. But as Hugo pointed out, we know that they're both equal to the same d. So now we have 2 620 times 10 to the minus 9 equals 3 lambda. So that cancels that, and we have our answer. Lambda equals 2 over 3 multiply 620 multiply 10 to the minus 9. What's 2 over 3 of that? 413 times 10 to the minus 9. Yeah, but I didn't put a point in.
Oh, yeah.
413 nanometers. The last part is, what is the small d? Wait, is that the last part? Yeah. Oh, okay. So we can actually know what the d is from this formula, yeah? So can you type that in? What do you get for d here?
It should be 1.93.
For the small d is, what is it?
1.93
times
10 to the minus 6
6.
meters.
Yes, of course, yeah, I figured that part out. Then we want this in millimeters first. So that's d equals 0.00193 times 10 to the minus 3. So that equals, d equals 0.00193 millimeters. So what I'm saying is here, the distance here is d. So in 1 millimeter, how many lines do we have? Well, all you do then is do 1 millimeter divided by 0.00193 millimeters. That's how many you have in 1 millimeter. So what number do you get here? Yeah, that's normal value here. 500 and...
18,000 images.
Wait, 1,000?
Yeah.
I feel like something went wrong here. No, maybe it's right. What is it? 500 and...
518,000 images.
518,000. Yeah. Alright. If that's what you got. Are we sure about this small d here?
Yeah.
Yeah, okay, fine,
How
fine.
to get it,
Which one?
the green card?
Just from here, just put this in on the calculator,
Okay.
that's all. Alright, we're finished there, so we've done which questions? 1, 2, 3, 4, isn't it?